All right, let's talk about energy. Energy for a long time was thought to be continuous, meaning that as a light bulb produces light, it was producing all photons of color simultaneously, and then we get, say, white light. Eventually, with the inception of hydrogen-filled lamps, we saw previously that hydrogen produces 3 discrete lines. So what does this mean to produce discrete lines and have all this empty space? Well, here's a quick way to think about the differences. Initially, with classical physics, we assumed that light was produced like running down a ramp. So as an electron moves down a ramp, it produces all kinds of photons. So producing Roy G. Biv continuously and forever. And in reality, this is probably true for, let's say, an incandescent bulb, where we have a filament where the electrons go in and electrons go out. So it probably is a very good indication because we are getting all kinds of photons getting produced from that light bulb. What we saw a moment ago with, or at least in a separate video, is that hydrogen lamps are a little bit different. So if you put hydrogen atoms, and in this case hydrogen molecules, into a lamp, they only produce certain colors of light. So there was a couple streaks of light that was showing from this lamp through a prism from a spectroscope, as we'll see in lab. So if this is what happens for hydrogen, it happens differently for different elements. And what does that mean? Well, what scientists believe is that instead of being a ramp, maybe it's more like a staircase. So your electron sits in what we call a ground state. And when it's excited by electricity, which is why light bulbs turn on, is because we allow electricity to flow through them. As they hit hydrogen atoms, they get excited and they jump to this new position. We can't see the jump, but eventually when they go from their jump back to home, they produce a photon. So the production of that photon is what we see eventually as light. But the reality is they can jump from this space to this space, from their ground state to an even higher excited state, or even to a higher excited state. Any of those are possible, and that's what we see as these indiscrete line spectra kinds of concepts, or these photons. In all situations, they can come back all the way down. Sometimes they can come back halfway and then go all the way down. So it doesn't have to happen in one step, but in each one of those steps, you produce a photon of light. So we can't see the jump of the electron. We can't see it being excited. But when it absorbs that energy into its new location, it can release it on its way back to its ground state. And that's what we can see and what we do see. And because of the distance between space to space, this distance between the first step and the second step, that distance is a quantity of energy. Therefore, we have quantum physics. So we've expanded the idea of what energy is because now we see with elements that their electrons kind of jump from place to place. They're not just continually moving place to place. They're in a certain location for a majority of the time, and only when they're excited from an outside source like electricity do they jump to a new location. So Bohr was the first scientist to kind of put all these pieces together. His idea is that it was much like the sun. So instead of saying our Bush Stadium concept, he was more in the idea that here's the sun in the solar system. This would be our nucleus. And then around it is orbits. And what you'll notice about these orbits is they just keep getting bigger and it looks kind of like a target. But it turns out that our idea of what an atom is was pretty close. This would be like the boxing match, the center of the Colosseum if this were ancient Roman times. And then we just have people sit in these little chairs along the way. And it turns out the further you get away, the more people you can sit there. If you're really close to the action, maybe you can't hardly fit anybody at all. And this is exactly what happens to our periodic table. We start to realize that as we're close to the nucleus, we can't fit very many elements that close because this space is very small. It's 1/20,000th the size of the atom, and that's 1/1,000,000th the size of a piece of hair. But as we continue to get away from the center of the atom, our atom has more, volumetric space, and therefore we can handle more electrons in that space. And that's exactly what Bohr saw. He thought of this orbit idea around the sun would be the most similar kind of model to think about. Although this would be more of a two-dimensional approach, you'd have to imagine that this is, like a sphere where you have some, shading here, and then it gets, round like a ball, so to speak. So your nucleus is really in here, and then you have these basically shells in a sense. So it's like layers of an onion more than it is a two-dimensional slice like we show in this picture over here. So again, remember, an atom is 3D, not 2D. But the orbit concept is the same. So what does it mean then to be excited? We might be excited for this lecture to be over, but the reality is, to be excited for an electron, what we have to worry about is, how do they excite? So if energy comes in, it comes from an outside source, say electricity. So here's your electricity coming in. This was your normal orbit. And what happens is your normal orbit is now changing because you are getting more energy, and that shot you up. So it's kind of like saying, if you were to tase somebody with a taser in their chair, they're going to jump out of their chair. And that's exactly what's happening here. Eventually they realize that they're safe, and where they used to be is their excited state, but where they would really like to be is their ground state. So eventually they go back home. And that's what we're seeing in this particular slide. So better yet is this picture, again showing you this idea that you're in this lowest energy orbit. That's your ground state. That's that kind of red circle. And then eventually you can be excited to this higher energy state. Just remember that when this happens, the most important feature of it is, as you go back down to home, you're going to return that energy, and that's going to be your photon. So every time you drop an energy, you're going to release that amount of energy as a photon that can be seen, and that's what we're seeing in our light bulbs, especially with our elemental light bulbs. So Bohr's model is basically how we set up the periodic table. You can imagine that if we have this spherical atom, it's a lot like our spherical globe. So if we take our planet as a whole, it's a sphere. We have a kind of round circumference, basically like a ball. But if we want to flatten this into a map, what happens is we get some distortion. So notice in a lot of maps, Antarctica kind of encompasses the whole area because it's taking up all those wedges that would be there if we were to take a sphere and hammer it flat. And you also end up making, Greenland look twice as big as it needs to be. But you can imagine we do that the exact same way with an atom. We take an atom with its orbits. Here they're doing the first 5 periods, so these shells are really just periods of the periodic table. And we're doing the exact same thing if we were to flatten this into a map. What it ends up looking like is the periodic table. So it's these little corners that are kind of pinched together close to the nucleus. So it's, it's this position here and here, the hydrogen and helium, that are basically here and here around the nucleus. And then as we get a little bit bigger in the periodic table, we start to see that we can fit more electrons around it. And from there, we just keep getting bigger. Because remember, down here, eventually the periodic table gets really big when those lanthanides and actinides jump down, and we get even bigger underneath. So this idea is just like mapping the atom, just like mapping the globe. We get a little bit of distortion, so the top looks kind of narrow and the bottom gets out. So that's really just going from that three-dimensional model of looking at the nucleus and then spanning out, and that's really just spanning down our periodic table. So you can imagine that the closer we are, the fewer electrons we can hold. Mathematically, this represents 2n squared. 2n squared tells us how many electrons can fit. So if you take 2 times energy 1 squared, so 2 times 1 squared, you can only fit 2 electrons. That's basically hydrogen and helium right there. If you go to the next one, you're going to see that this is now going to be the next 8 electrons, the next 8 elements in the periodic table. That's our second row here. And that's exactly what we're expecting to see for, say, lithium through neon. The larger we get, the more electrons that we can hold, and this works really well until we get to period 4. Period 4 and period 3, we start to see this not fit as well as it should. We don't actually see 18 electrons until period 4, which is a problem. So scientists had to figure out why doesn't it fit perfectly to this model. And again, this was a hypothesis, and we're about to see that that hypothesis wasn't completely true, but it was in the right direction. So what we do know is that there are things that are like orbits, like shells, basically like layers of an onion, so to speak, from this three-dimensional stadium. And that we can fit a certain amount of electrons in them. And it works really well for the first 2 periods, specifically because we get 2 and 8, just like we would mathematically predict. But then in period 3, we'd expect 18, and we don't see that. We don't see that until period 4. And for the 4th period, we'd expect 32 electrons to fit, and that doesn't happen until, say, period 6. So what's going on? Well, what's most important about any of this is electrons that are on the outside. Those are the ones that determine chemistry. These are the ones that we've mentioned before. What's most important about this, before we answer that question that we posed just a moment ago, is that valence shells, the easiest way to look at those is the Roman numerals. Roman numerals will tell us everything we need to know about what's on the outside. So if you look at lithium and sodium, and the reason that Mendeleev was so successful at putting them together is they're both going to be in Roman numeral 1 because they have 1 electron on the outside. Because the reality is, just like people, you only see what's on the outside. You don't see what's on the inside. You can't tell if somebody's an axe murderer by looking at them. You'd only have to see that on the inside, and that's not something that we can see easily. We have to get to know the person. So when we see elements, just like when we see people, we see what's on the outside. We see their clothing. And the clothing here for elements is their valence shell, their outer shell. So these are the ones that are most important, and these are the ones that determine their chemical properties. And that's what this textbook is about. So as we apply these ideas to our line spectra, again, we're back to this idea of why do we see discrete lines? Well, again, that's because they jump from place to place, from chair to chair. There is no space to sit between chairs, so to speak. So that's the empty space that we're seeing. We mentioned the ground state. That was the original location of the electron. So that's as it sits in the periodic table. And then any open chairs, any open boxes of the periodic table, those would be fair game to be excited towards. We can't see the jump. We can only see the fall. When it falls back to its ground state, we see that energy being released as a photon of a specific color. So in this slide, we're going to see the answer to what was happening. As we get further away from the nucleus, we actually get closer together because we're starting to overlap. So you can actually kind of see this in the sense of Bohr Stadium, because as we get further away, we have chairs that are very close to each other. We have chairs that are on top of chairs in the sense of balconies and mezzanines and so forth. So the reality here is the distance between 1 and 2 is pretty huge, but the distance between 2 and 3 is small, and then it just keeps getting smaller from there. So as we jump between levels, a lot of those levels up here are really close, so their energies aren't a lot different. So their wavelengths of color that they would produce would be very small. But if you were to fall back to, say, 1, that would be a large amount of energy produced because that's a large distance. So to fix this issue of why isn't there 18 electrons in 3 or 32 electrons in period 4 of the periodic table, Bohr decided upon subshells. Subshells just means that there are sections. So now it starts to feel a whole lot like a ticket to, say, a stadium. If you were to buy a ticket to a stadium, what we'd expect to see is it's going to have some kind of row number. That row number equals the period on the periodic table. It would also have a section number. And that section number is basically the sublevel or the subshell. And if you wanted to think of a period as a shell, that's fine too. So then beyond that, all we really need is a seat number. And really that's just the box on the periodic table itself. So the periods are basically 1 through 7. Those are our horizontal lines from top to bottom, from hydrogen all the way down to francium. Our subshells are basically these just regions of the periodic table. We have that tall tower, we have that rectangle, we have that square, and then underneath we have the other rectangle. So those are all sublevels. We happen to call those sublevels, and they're mentioned in the slides coming up. Those are going to be our S, P, P, D, and then F. So we'll see those coming up. But the take-home message here is it's a lot like a ticket to the stadium. You have a row number, you have a seat number, and section numbers. So 3 criteria to look for. What row are you in? What section are you in? What seat are you in? And that's really the bulk of this particular chapter, as long as we can keep our sections and rows straight. So as we look at these sections, we start to see that the more sublevels are going to show up with our higher energy levels. So the further we get away, we can start to have more sublevels or subshells because there's more three-dimensional space available. Very close to the nucleus, where S is, there's not much space, so there's only one section and only one row. But as soon as we move out to the second row, we're going to start to see 2 sections or 2 subshells, and that's because we have more space. 3 has even more, 4 has even more. So what we start to see very quickly from that is certain amount of electrons can be held, and that's the size of the section from the periodic table. So the easiest way to see this on a periodic table is if we were to look at the S, P, D, and F of the periodic table. Let's do that quickly. So notice as we look at our periodic table that we get on the exam, we see very quickly here's our section of S. So this is what we call the S. And notice that there are only 2 boxes, 1 here, 2 there, down the entire section. Then we go to our P section, and again, helium is basically over here in this idea. Over here, you'll notice that we have only 6 seats in this section, and that's what we're after. That's all that can fit in that section. Next would be, and again, this was what we call the P section. In the middle is what we call the D section. In it, we can hold 10. And those are our transition metals. And then underneath, eventually after lanthanum and actinium, we see those lanthanides and actinides under here. Those are our Fs, and we can fit 14. We don't really see these much at all in Introchem because it's pretty deep into the periodic table. And a lot of those are radioactive, but for purposes of the concept, realize that's just another section. It happens to be one of the longest sections of the bunch. But again, just another section overall. So this is the breakdown of our stadium. Here we have row 1, row 2, row 3, row 4, row 5, row 6, row 7. And then here we have sections, and then each individually is our seats. And that's the best way to understand what scientific method that we're kind of using here is orbits. Now sublevels, our orbits are basically these periods, and now our sublevels or subshells are these S, P, D, and F kind of sections. So if you want to know how many electrons can hold in each sublevel or subsection or subshell, just count boxes. That's the fastest way. So eventually we have an issue. we have all these electrons piling up at the outer edges of our periodic table, which is at the outer edges of our stadium. And this is what happens. We have an overlap. In reality, we would call this overlap a balcony. So if we have a balcony, it's because we have this D and this S electrons that are now being overlapped. The 4 gets a little too low, the 3 gets a little too high, and they overlap. So this balcony or this mezzanine is exactly what you see in Busch Stadium. If you want to fit more people in the stadium, you just put seats on top of seats, just three-dimensionally higher. And that's exactly what we see in our atom because they too are three-dimensional. And this leads us into electron configuration. An electron configuration is basically just a ticket to the stadium. So in a separate video, we will show you how to tackle this. It'll get us out of this history lesson that we're kind of stuck in now and put all the pieces together and what that ticket to the stadium looks like, or that ticket to the periodic table looks like. So we'll see you then.